In this section of chapter 19, I would like to discuss about uh, calculation of entropy, and also we are going to define a new quantity called free energy, and also we'll show you how to calculate free energy change and what information we can get from free energy change. First, calculation of entropy or randomness. Now, whenever there is a superscript 0, that means it's a standard change in entropy. By standard, we mean a pure substance under 1 atmospheric pressure. And these values are listed in the back of the book. This calculation is quite straightforward. Like if I know the product values, so all the product values multiplied by the number of moles of products minus reactant values multiplied by number of moles of reactants, and that would give me change in entropy or randomness. And of course, these are all standard values because that means you get these values from back of the book. Under standard condition, these values were obtained. Let's go over a problem. This is 53D. In this reaction, you can see that there are 2 moles of methyl alcohol reacting with 3 moles of oxygen, giving 2 moles of carbon dioxide and 4 moles of H2O. In order to explain this, I copied these values from back of the book. So 237.6 is for methyl alcohol. It's the joule per mole per Kelvin. And for oxygen, the value is 205 joule per mole per Kelvin. And then for carbon dioxide, it's 213.6 joule per mole Kelvin. For H2O, it is 188.83 joule per Kelvin per mole. Now, first we must have product values, 4 times the value for H2O. Why 4 times? Because there are 4 moles of H2O. And 188.83 goes with joule per mole, and 4 mole times 188.83. So that's what we're doing here. That's joule per mole per Kelvin. And then we have 2 moles of CO2. That's 2 times 213.6. That's 2 is coming from coefficients of balanced reaction. You can consider it to be 2 mole. So 2 mole times the value for carbon dioxide, and minus, always keep in mind the products are all added and reactants are subtracted. Now 2 times 237 is for the first reactant, minus 3 times the value for oxygen, 205. And if you keep track of units, this 2 is mole, so 2 is mole, 3 is mole, and the numbers, other numbers like 213.6, 237.6, and 205 have the unit of joule per Kelvin, joule per mole times Kelvin. So mole would cancel out, then you get joule per Kelvin. I'll show you one such cancellation of unit. Moles cancel out with moles here. So in each case, unit would be joule per Kelvin. In this slide, we're showing you a second method of calculating change in entropy. In last slide, we talked about how we can get change in entropy from standard entropy values. Those are pretty well-known values, by subtracting all the products minus the reactants. In this case, we can calculate in a different way. Q is the amount of heat added slowly, and T is the temperature. So if I know the amount of heat being added, and I also know the temperature at which the heat was gradually added, then I can calculate the change of entropy or randomness in the system. Now, this is the review of what we just mentioned in section 1 of this chapter, that spontaneous process results in an increased entropy or randomness. of the universe. So that's system plus surroundings. But there is a problem with this criterion. About the surroundings, it's very hard to know entropy changes within the surroundings, because there are so many things around the system that make surroundings. So it's very hard to keep track of entropy changes or randomness changes in surroundings. So scientists thought about a new criterion that can be applied to the system only. That means without taking into account surroundings. And that's why we need to define a new quantity. This new quantity is called Gibbs free energy, or represented by G. Now this is how it is defined. This is pretty much, you can consider to be a mathematical quantity, but this gives extremely important information about whether a reaction is going to happen spontaneously or not, a process is going to happen spontaneously or not. Let me first explain to you how we can calculate a Gibbs free energy. Gibbs free energy is made up of two components. H is enthalpy or heat content, and the other quantity is T times S. S is entropy, T is the temperature in Kelvin. So delta G would be given by delta H minus T delta S, where delta H, you already know about delta H from your previous chemistry class, is change in enthalpy or heat content. Now, most important information we know about from delta G is whether a reaction is going to be spontaneous or not. If delta G is negative, reaction will be spontaneous. If delta G is greater than 0 or positive, reaction will be non-spontaneous. That means it's not going to happen. You'll have to force it to happen. When it is equal to 0, you'd get equilibrium. Here we're going to discuss how to calculate delta G, or change in free energy. Again, there are more than one way one can calculate delta G value. We can get free energy change in a reaction from standard free energy of formation values. Again, those are listed in the back of the book, and it should be pretty straightforward. Pretty much the way you calculate change in entropy from standard entropy values. So this is like a delta G F0 stands for change in free energy of formation. N is the number of moles that comes from the balanced reaction. So again, just like before, product values minus the reactant values. Now standard state is defined to be the pure solid state for solid. For gas, under 1 atmospheric pressure. For liquid is a pure liquid, and temperature is 25 degrees centigrade, or it's 298 Kelvin. That's one method. The second method is from delta H and delta S values. So I can calculate change in free energy from change in enthalpy and times temperature in Kelvin times change in entropy values. The third method would be change in free energy calculation at any pressure value. The first part is standard value, standard state value. So that's like products minus reactants times the moles of products and moles of reactants that we defined in last slide. In addition to that, you need to add RT. R have the value of 8.314 joule per mole per Kelvin. T is the temperature in Kelvin, and log of Q is the same Q value that we talked about before. The Q would have product concentration, if you're talking about in terms of concentration units, on the top, raised to the power coefficient of balanced reaction, reactant concentration on the bottom, raised to the power coefficient of balanced reaction. And that gives you delta G, or free energy change of a chemical reaction under non-standard situation. So non-standard means pressure, say pressure is not 1 atmospheric pressure. Say it's 2 atmospheric unit, 2 atmospheric pressure. So in that case, you first get a standard value and then add this quantity, RT log of Q. That would have all these values for non-standard situation. We can also calculate equilibrium constant by setting Q equals to K equilibrium. Change in free energy would be 0 at equilibrium. We define that for a spontaneous process, delta G is negative. For non-spontaneous process, delta G is positive. And for equilibrium, remember equilibrium, neither direction will be favored. Forward reaction equal to reverse reaction. So at equilibrium, delta G is equals to 0. So when I set this, we can consider this delta G reaction to be 0 in the top of this reaction. Let me show you with the arrow. And then do simple algebra. We are going to get delta G0, or standard free energy change of a reaction, is given by minus RT log of K equilibrium. And that's Q becomes equilibrium constant because we considered equilibrium situation. So in other words, if I know the equilibrium constant, if I know the temperature, R is well known, is a constant, 8.314, I can calculate change in free energy, standard change in free energy. Let's go over number 82C from the book. That's page 822. Now here we're calculating standard free energy change of a reaction from standard free energy of formation values. Again, you get these values from back of the book. So this is the reaction we are focusing on. There are 2 moles of products, and that's why 2 times the value of formation, free energy of formation of that particular product, which is SO3, minus 2 moles of SO2, because there are 2 moles. And again, this is the formation value, free energy of formation value, you get it from back of the book, and minus the formation value for oxygen. Now for pure element, free energy of formation is 0. Let's do number 57 here. In this problem, they have given you delta H value, which is minus 35.4. And also change in entropy value, which is minus 85.5 joule per Kelvin. And temperature is given, which is 298 Kelvin. First, the question is, part A question is this reaction exothermic or endothermic? How do I know that? Just look at this value, delta H value. When it is negative, heat is given off or energy is given off, and that's exothermic reaction. So in this case, we get a negative value, and that's why it's an exothermic reaction. Part B. The question is, does this reaction lead to an increase or decrease in randomness or disorder of the system? So the question is, what is happening here with entropy? Again, we get this value, interpret that based on this number, minus 85.5 joule per Kelvin. That's the change in entropy. So entropy is negative. Negative means final entropy is smaller than the initial entropy, or entropy decreases in this reaction. So this is the answer. For the third part, you need to calculate delta G0, standard free energy change for the reaction at 298 Kelvin. Now, how do I calculate that? Information is given about delta H and S0. Delta is 0. So we are going to use those numbers in order to calculate delta G0 value. So let's plug in those numbers. Pay attention to the unit. So the first one is minus 35.4 kilojoule. Next one is, I'm going to write down minus, the way it appears in that expression, minus, then T is 298 Kelvin times delta is 0, which is minus 85.5. Now that's joule per Kelvin. We have to make it kilojoule just to be consistent with the unit. So divide by 1000, because 1000 joule makes a kilojoule. So that's kilojoule per Kelvin. Now we have every unit consistent. We can subtract it. Now that gives you, if you do the math, you're going to get minus 9.92 kilojoule. So in part D, the question is this reaction is spontaneous at 298 Kelvin under standard conditions? Since we got a negative value of delta G, remember I mentioned that delta G negative means spontaneous reaction. So this reaction is going to happen spontaneously. In problem number 66, we're looking at a reaction. The value of delta H is given, or change in enthalpy of this reaction is given. Entropy change is also given. Temperature is also given. So you need to first calculate change in free energy, standard change in free energy. And we already know that expression, delta G, let me write down here, delta G would be given by superscript 0 for standard state of reaction equals to delta H0 of reaction minus T delta S0. So basically we plug in all these numbers. So delta H is 572. It's endothermic reaction because that's positive. 572, that's kilojoule. So keep that in mind. This is kilojoule minus T, 298 Kelvin, times delta S is, we need to change it from joule to kilojoule. So 179 divided by 1000 to get kilojoule. So now it will get kilojoule per Kelvin. So kilojoule per Kelvin. I'm running out of space there. And so that gives me delta G of reaction value. Let me write down here. Delta G 0 of reaction. Use your calculator and you get 518.7. That's what I got. 518.7 kilojoule. And this is positive. Remember, for spontaneous process, delta G has to be negative. Since it is positive, so it's not going to be a spontaneous process. So this is going to be non-spontaneous at this particular temperature of 298 Kelvin. What that means is, when you maintain temperature as 298 Kelvin, this reaction is not going to happen. Now, the important part of the question is, if the reaction is not spontaneous, and we know it's not, at 298 Kelvin, at what temperature will the reaction become spontaneous? So here we can vary the temperature. Delta H is known, 572 is fixed. So this temperature, rather than doing experiment at 298 Kelvin, I can do the experiment at a higher temperature or a lower temperature. Now the question is, what will be the temperature at which delta G would become negative? That means at that temperature, reaction would happen spontaneously. So basically what you need to do is, we know that I have delta H value is 572. So this part, second part of this problem, has to exceed 572. So let's first calculate when this part would be equal. So any temperature above that is going to make this second half exceeding 572. Let me make it clear. So in order to do that, we'd set delta G equals to 0. this would give me delta H0 minus T delta S0. So basically we're setting these two equal, and we already know that delta H0 is 572. So I can write down delta H0 is 572 kilojoule equals to, instead of writing 298 Kelvin now, I'm just going to write down T now, because we don't know at what temperature this is going to happen. So let's have temperature as T, and we already know that this is delta S is 179 divided by 1000, or 0.179 kilojoule and per Kelvin. Now from here I can calculate T. So keep in mind, this will be the T, or temperature, at which we get delta G equals to 0. Now we will have to get negative, so T has to be greater than what we're going to get now. So let's plug in these numbers. 572 divide by, we're working on this, right? 572 divided by 0.179. 572 is kilojoule, and 0.179 is kilojoule per Kelvin. So that gives me Kelvin, and the unit checks out. So the temperature is 3196 Kelvin. So close to 3200 degree Kelvin. What it tells you that temperature has to be greater than this. So in order to be spontaneous, so for a spontaneous process, temperature will have to be greater than 3196 Kelvin. Any temperature above 3196 would make the right hand side quantity bigger than 572. And since there is a negative sign, that means delta G is going to be negative, and that negative means a spontaneous reaction. So answer to this question is any temperature higher than 3196 or around 3200 Kelvin is going to make this reaction spontaneous. In problem 79, a chemical reaction is given. Let me first write down that reaction. 2 NO2, and that's in the form of gas, giving N2O4. N2O4, that's also gas. In part A, they're saying that by using the data from Appendix C, calculate delta G0 value. Since we're going to need this value for doing part B, so let's first calculate delta G0 value. Delta G0 value for the reaction is also called standard free energy change. And we get the values of standard free energy of formation of products, which is N2O4, and subtract the reactant value. Of course, you need to multiply by the number of moles, because those values are given in kilojoule per mole. So let's do that. So this is going to be my expression, delta GF0, again product value first, minus the reactant values, 2 times the reactant values, because there are 2 moles. In this case, N2O4 there is 1 mole, but for N2O4 there is 1 mole, and for NO2 there are 2 moles. Okay, so now 1 times N2O4 value minus 2 times NO2 value. Now I'm going to use these values from Appendix C, and the value for N2O4 is 98.28. 98.28. That's kilojoule per mole times 1 mole, because there's 1 in front of N2O4, so that gives me kilojoule. minus 2 times the value of NO2 is 51.84. Again, these are all from Appendix C. This gives me minus 5.40 kilojoule. So standard free energy change for this reaction is minus 5.40. In part B, they're asking you to calculate delta G at 298 Kelvin when partial pressures are not 1 atmosphere. So in other words, we're talking about calculating delta G for non-standard situations. So let me use a different pen. So for part B, we're going to calculate delta G for non-standard condition. Remember, for a standard condition for gases, it has to be 1 atmosphere. So in this, the pressures for N2O4 and NO2 are not 1 atmosphere. So it's not under standard state. So you're going to solve it by using 2 different parts in this expression. Delta G will be given by delta G0, a standard free energy change value, plus RT log of Q. Delta G we already know. Delta G0 we already know from part A. So I'm just going to use that number. So that's going to be minus 5.40 kilojoule. Okay, it's a good idea to write down the unit, it's kilojoule, plus RT. Our value is 8.314. 8.314. Now that's in joule per Kelvin per mole. So we need to change it in kilojoule. So this is joule per Kelvin mole. And I'm going to change it to kilojoule to be consistent with kilojoule on the left hand side. So in order to make it kilojoule, divide by 1000. Because 1000 joule makes a kilojoule. And that's our value in kilojoule unit. Temperature is in Kelvin, that's 298 Kelvin. And then log of Q. Remember the Q product on the top, reactant on the bottom. Let's first write down the Q expression. So this is expression for Q. Q is written pretty much like equilibrium constant, except these are any concentration other than equilibrium values. So it can be pressure of N2O4 divided by pressure of NO2 squared. So you treat pressure pretty much like concentration. Remember, we had concentration on the top for the reactant and concentration of the product on the top and reactant concentration on the bottom, and raised to the power coefficient of balanced reaction. When it's given in pressure unit, then obviously pressure units would be there instead of concentration. Remember that pressure and concentrations are related to each other. In gas sample, more concentrated gas sample means more molecules of gas, also higher pressure. So higher pressure goes with higher concentration. So don't get confused when you write down the Q expression. And so the Q expression in this case is given by this quantity. So this is Q. Because N2O4 is the product, NO2 is the reactant, and Y squared because there are 2 moles of NO2. This is 2 moles of NO2. Now, the values that go into N2O4 and NO2, I mean, that's already given. So let me show those numbers. Minus 5.40, that's kilojoule, plus 8.314 divided by 10 cubed. This is kilojoule per Kelvin mole times 298 Kelvin times log of, Now you now need to plug in those numbers, which would be 1.60 on the top, that's given, atmosphere, divided by 0.40, that's also given, atmosphere, and that's squared. So that gives me log of 10. This is, remember that this is a log with respect to base 10. So now I'm going to write down this whole thing. I mean, make sure you recheck this calculation of mine. Minus 5.40, it's already, we already know, plus 5.70. And that gives plus 0.30 kilojoule. And that's the answer, because they wanted to know change in free energy under non-standard condition when pressure of N2O4 is 1.60 atmosphere and pressure of NO2 is 0.40 atmosphere. Here we are qualitatively looking into a problem and trying to predict whether a reaction is going to be spontaneous or non-spontaneous, and under what condition it may change from non-spontaneous to spontaneous, just by looking at the reaction and the delta H value or the sign. The first reaction is reaction of ozone breaking down into 3 moles of oxygen. Only given information is delta H value is negative. In other words, it's an exothermic reaction, so that's known. We need to figure out what is the delta S value. Is it going to be positive or negative? In other words, is entropy going to be increased or decreased? We start with 2 moles of ozone but end up with 3 moles of oxygen. So number of mole has increased. Remember, we discussed before, in a given volume, when number of mole is increased, entropy is increased. So final entropy is increased, so you'd have 3 moles of O2 at the end and 2 moles of O3 at the beginning. So final is greater than initial, so it's going to be positive. So that's why delta S is positive and entropy is increased. Now let's try to get an idea about whether this reaction is going to happen spontaneously or not. We already know that delta H is negative because it's given. Now temperature can never be negative because you're talking about Kelvin scale. And delta S, we already know this is positive, so this is positive. Temperature is also positive. The whole thing is positive, which is subtracted. And delta H is negative. That means delta G is going to be negative no matter what value of T we have. So in other words, delta G is always negative for this particular reaction. That means this reaction is going to be spontaneous at every temperature. Now sometimes non-spontaneous reactions are forced to happen by another reaction. That happens in biological system. For example, ADP, adenosine diphosphate, in presence of energy changes to ATP, adenosine triphosphate. Normally this is not going to happen. However, the top reaction, glucose, when reacts with oxygen, I mean that happens like in all the starchy compounds that we eat that breaks down into glucose and that goes through our bloodstream, and then in every cell it reacts with oxygen that we breathe in, and that gives carbon dioxide, water vapor, and energy. So this is an exothermic energy, and that energy is used up in converting ADP, adenosine diphosphate, into adenosine triphosphate. So ATP changes to ADP and energy will be released when there is need for it. So ATP pretty much stores that energy or free energy in this case.